Good morning, everyone. We are Team Max, and we will be participating in the Payload Delivery Challenge. A brief overview of the challenge. We have 3 targets put out on the field like this. There's going to be obstacles in front of each target. Each target is going to be its own specific color, yellow, red, and blue. Each one is also going to be putting out its own RF signature or radio frequency signature, and we will also have the GPS coordinates of each one. For the first part of the challenge, we have to go to each one of these targets and drop a payload within 10 feet of each one, and then return to the starting point within 2 minutes. For the second part of the challenge, we have to go to only one of them and drop the payload again within 10 feet and be the first ones to do that. We will identify which one is the target to be dropped by the radio frequency signature of that particular target. The other 2 will be turned off for that part of the challenge. To accomplish all of this, we have created RACs.
This is our land-based closed-source solution for the payload challenge. For the physical aspect, the RACs was built on the Red Cat Volcano EPX RC truck platform. This platform provides us with a 7.2 volt 2000 milliamp hour nickel metal hydride battery, DC brush motor with electronic speed control, 4-wheel drive with conventional steering, aluminum cap oil-filled suspension, and a sturdy plastic construction, making it ideal for off-road operation. This vehicle has been outfitted with a variety of sensors in strategic locations to optimize their performance. These could be subcategorized into 3 categories: navigation, avoidance, and target acquisition. In the front, we can see the LiDAR and the sonar sensors to maximize obstruction detection. At an altitude is the visual sensor with a negative angle to expand its field of view. The RF receiver, digital compass, and GPS are as far away from the motor to avoid electromagnetic interference, and the payload delivery module is at the back to unload cargo while on the move.
My name is Connor, and I'll be talking about the RACS block diagram. The RACS block diagram was broken down into a modular way where we could separate a large problem into more simpler solutions. As you can see, we have subsystems that are taking in sensor data and sending that to our main microcontroller, which controls the motor, our payload, and our mobility, which is our steering. The GPS microcontroller receives the compass and GPS information via UART and SPI communication. Our avoidance microcontroller is getting information from the LiDAR and ultrasonic information to avoid obstacles, while our RF microcontroller is telling us where in the proximity is our target and which target it is coming, the signal is coming from.
My name is Sean. Once we require the GPS location on the challenge day, we'll have the digital compass magnetometer as a guidance to our car, and we'll use avoidance sensors to avoid any obstacles on the way. Once we reach the payload location, we'll use the vision camera to take the control of the ESC and servo to get to the closer proximity of the drop zone location. And once we deliver the payload, the ESC and servo will maneuver to the next GPS location. And for the second part of the challenge, we'll use the RF for target acquisition, then repeat the same process.
Our navigation system updates about every foot at 10 miles an hour, which is about every 50 milliseconds. It receives RMC data via the GPS and compass information 0 to 360 degrees from our compass. Our microcontroller then parses that information and converts it to a Cartesian format and passes it in a nice formatted packet to the main microcontroller to interpret that data. Once that data is taken from the main microcontroller, once it's in the main microcontroller, the data is then filtered to find the actual best location that is most likely from where you were heading before. It is then taken all that information and make real-time decisions on the next location to drive to.
Good morning, everyone. My name is Taylor. I've designed the RACS RF subsystem, and as mentioned before, the primary purpose of this system is to identify the active target in the second portion of the competition. To do so, we'll make use of Micrel's MicroRF 220 receiver IC, as you can see here on the screen. Each target which provides us with a squelch feature to reduce the noise on the demodulated output signal that it provides our PIC16 for processing. Each target transmits a unique signal frequency ID, so red for 880 hertz, yellow 1.2 kilohertz, and blue 1.3 kilohertz. We'll send this demodulated output signal, to the PIC16 microcontroller, where we use the input capture mode to time the signals, determine the frequency, the period, and process these signals, which will communicate digitally with the main microcontroller to indicate which target is active, so we can update the GPS, motor controls, and steering control systems to navigate smoothly to our active target. Thank you.
Hello, everybody. My name is Roger, and I'll be discussing motor control. So, after acquiring our target and determining an optimal path to our destination, our main microcontroller will send signals to an ESC and steering servo to control both the speed and direction of our vehicle. We achieve this by using the PIC32's output compare feature to create specific pulse widths that range between 0 and 2 milliseconds. By varying these pulse widths, we were able to develop multiple speed settings and have a higher resolution while turning. This simple drive system, combined with our other sensors, will allow us to move autonomously on the field.
So my name is Jessica, and I'll be talking about the avoidance subsystem. The avoidance subsystem consists of one LiDAR sensor and two ultrasonic sensors. The LiDAR sensor serves as our primary proximity sensor, whereas the ultrasonic sensors are placed on either side. The LiDAR sensor works by sending out a near-infrared signal, laser signal, and taking the time delay from the signal that is reflected back. We utilize timer gates on the PIC16 to measure the pulse width of the signal that is reflected back, and then we calculated the distance based on the speed of light. Once an object is detected within 5 feet in front of the sensor, we send a pulse to our main microcontroller that there's an object in front of it, and the two ultrasonic sensors on either side are triggered to send out a pulse, and they measure to see if there's anything on either side. The ultrasonic sensors work similar to the LiDAR sensor. However, instead of sending out a laser pulse, they send out an ultrasonic pulse, and their distance is measured using the speed of sound instead of the speed of light. All of these sensors communicate to our PIC16 through digital pulses, and this data is then forwarded on to our main microcontroller.
Hi everyone, I'm Ryan, and I'm going to talk a little bit about our drop zone detection. Since our challenge consists of 3 colored targets, we are in need of a color sensor. We chose to fill this need with the Pixie camera. It's a color detecting camera that can be taught to detect specific color signatures. In our case, red, yellow, and blue. Using this capability, we communicate directly to our main microcontroller, giving it computer vision. From our computer vision, we're looking for 2 signals. One is the detection flag, telling our vehicle, hey, I see the target, I'm going to take over the motors. And 2 is the position of the target. Using the X position of the target, our computer vision works with our ESC to navigate for optimal position for payload delivery.
Good morning, everyone. My name is Blake, and I'll be going over the payload delivery mechanism. So once we've reached our target, we need a reliable way to both store and deliver the payload. For our payload, we decided to use a poker chip-sized wafer. This allowed us to maximize our space efficiency on the vehicle. Our actual design features 3D printed ABS plastic and 2 stationary brackets that are mounted to the rear of the vehicle. The interior is a rotating fan that holds the poker chips. So as the fan rotates down through the servo's pulse widths, the poker chips will slide past this opening and drop down on the position. So the servo is connected to our main microcontroller, our PIC32, and once the GPS sensitivity, our current GPS sensitivity is within desired specification of our target GPS sensitivity, it'll send the correct pulse width to the servo that'll drop the correct payload. And I have a little demonstration here through SolidWorks. So as you can see, when the first chip drops, the later 2 are still protected in the system, so that proves the reliability of our system.
Good morning, everybody. My name is Marcus. So basically, these are our goals and our milestones. Our first goal was to learn the PIC32, which would be the microchip that would be controlling the main systems. We were able to do some research and discover all the peripherals needed to make this thing work. We were able to accomplish this thing by the end of February. Our next goal was to be able to drive our car in a figure eight. We were able to do that outside of the library by the end of March. On April, we did various tests and we integrated different parts of the system to make sure we worked. A main highlight I like about the system was we were able to get the color to sense the camera to sense the color and was told the car to drive, and it chased the color around. Now we are in the month of May, and we are doing our final testing to make sure that we get everything right, so by the time we get to the end of the competition, we are ready to compete. So our budget, we try to be cost efficient as possible. So our first thing we did, we made sure we bought a bunch of RC cars, around 35% of our budget. Our next was sensors, making sure we got the ultrasonics and the camera, which turned out to be about 44% of our budget. Our next is taxes and shipping, which we have to pay, and that was about 9%. And our last item, the miscellaneous items such as the servo and the payload dispenser, which was about 13% of our budget. So our remaining budget ended up to be close to $150. Now you could join us tomorrow as we show off our design at Design Day with all the other engineering classes. And this just ended. Ladies and gentlemen, boys and girls, this 2017 annual Payload Challenge will be coming to you this Thursday at E&S Field, right by the music building. Watch as Team Max takes on the Death Star of Team Vader and the non-conforming evil rebels of Team Resistance. Thank you for your presentation, and see you